Sodium is one of the most important S-block elements used in modern industry. Although sodium is a highly reactive alkali metal and is never found in its free metallic form in nature, its unique physical and chemical properties make it extremely valuable in several industrial applications. Sodium possesses excellent thermal conductivity, outstanding heat transfer efficiency, strong reducing ability, and produces an intense yellow light when electrically excited. These remarkable characteristics have led to its use in sodium vapor lamps, chemical manufacturing, nuclear reactors, metallurgy, scientific research, and the production of numerous industrial chemicals. The infographic highlights these major industrial applications and explains why sodium continues to be an important metal in advanced technology and manufacturing. One of the best-known industrial uses of sodium is in sodium vapor lamps, which have been widely used for street lighting, highways, tunnels, airports, railway stations, and large outdoor areas. In these lamps, a small amount of sodium metal is sealed inside a special discharge tube along with inert gases such as neon and, in some designs, a small amount of mercury. When electricity passes through the tube, the sodium atoms become excited and emit an intense bright yellow light with a wavelength of approximately 589 nanometers. This yellow light is extremely bright and highly energy efficient, making sodium vapor lamps much more economical than many older lighting technologies. They also have a long operating life and perform well under outdoor conditions, which explains why they have been widely used for road and street illumination for many decades. Although many cities are now replacing them with LED lighting, sodium vapor lamps are still used in certain industrial and transportation applications. Another major industrial application of sodium is in chemical synthesis and industrial manufacturing. Sodium is a powerful reducing agent because it readily loses its single valence electron to form sodium ions. This property allows sodium to reduce many compounds during chemical reactions, making it valuable in the manufacture of numerous organic and inorganic chemicals. Metallic sodium is used in the preparation of synthetic rubber, pharmaceuticals, dyes, perfumes, detergents, pesticides, and various specialty chemicals. It is also used in laboratories and chemical industries to carry out reactions that require strong reducing conditions. Because of its high reactivity, sodium enables many industrial chemical processes that would otherwise be difficult or inefficient. The infographic also highlights sodium's important role in nuclear reactors as a liquid metal coolant. Certain advanced nuclear reactors, particularly sodium-cooled fast reactors, use liquid sodium instead of water to transfer heat away from the reactor core. Sodium is exceptionally suitable for this purpose because it has very high thermal conductivity and transfers heat rapidly. Unlike water, liquid sodium remains in the liquid state over a very wide temperature range and has a very high boiling point, allowing it to carry large amounts of heat without generating extremely high pressures. This improves the efficiency of heat transfer and allows reactor systems to operate at high temperatures while maintaining relatively low pressure. However, because sodium reacts violently with water and oxygen, these cooling systems require specialized engineering and rigorous safety measures. Sodium is also widely used in metallurgy for extracting and purifying certain metals. Because sodium is a very strong reducing agent, it can remove oxygen and other impurities from metallic compounds during extraction processes. It is employed in the production of metals such as titanium, zirconium, potassium, and other reactive elements. In some metallurgical operations, sodium helps improve the purity and quality of the final metal products while increasing manufacturing efficiency. Another important industrial application of sodium is scientific research. Metallic sodium is frequently used in laboratories to study highly reactive chemical processes and to prepare specialized compounds for research purposes. Chemists also use sodium in certain analytical techniques and experimental procedures where strong reducing conditions are required. Although sodium must be handled carefully because of its vigorous reactions with air and moisture, it remains an indispensable reagent in chemical research. Sodium also contributes indirectly to numerous industrial sectors through its compounds. Sodium chloride, sodium hydroxide, sodium carbonate, sodium bicarbonate, sodium nitrate, and many other sodium compounds are among the most widely produced industrial chemicals in the world. These compounds are used in glass manufacturing, paper production, soap and detergent industries, textile processing, petroleum refining, water treatment, food processing, pharmaceuticals, and countless other manufacturing processes. Although the infographic focuses primarily on metallic sodium, its compounds have an even broader range of industrial applications. Several unique properties explain why sodium is so valuable in industry. It possesses excellent thermal conductivity, allowing heat to move rapidly through the metal. It exhibits high heat transfer efficiency, making it an outstanding coolant in specialized engineering systems. Sodium is also an extremely powerful reducing agent because it easily donates its outermost electron during chemical reactions. Furthermore, sodium produces an intense bright yellow light when electrically excited, making it highly suitable for vapor lamp technology. These properties combine to make sodium an important material in both chemical manufacturing and advanced engineering. The infographic illustrates the industrial pathway of sodium, beginning with its production from sodium compounds through electrolysis. After purification, metallic sodium is supplied to industries where it is used in chemical manufacturing, sodium vapor lamp production, metallurgical processes, scientific laboratories, and nuclear reactor cooling systems. These applications demonstrate how a highly reactive element can be safely utilized in controlled industrial environments to perform functions that many other metals cannot accomplish as efficiently. Because sodium reacts vigorously with water and oxygen. Strict safety precautions are necessary during storage, transportation, and industrial use. Metallic sodium is usually stored under kerosene or mineral oil to prevent contact with air and moisture. Industrial facilities handling sodium employ specialized equipment, inert atmospheres, protective clothing, and carefully designed safety systems to minimize the risk of accidental reactions. Although modern LED technology has replaced sodium vapor lamps in many cities due to improved energy efficiency and color rendering, sodium continues to play a vital role in chemical manufacturing, nuclear engineering, advanced metallurgy, and scientific research. Ongoing developments in fast breeder reactor technology and specialized chemical synthesis ensure that sodium remains an important industrial material. Sodium is a highly reactive S-block metal whose exceptional physical and chemical properties have made it valuable in numerous industrial applications. It is widely used in sodium vapor lamps for producing bright yellow street lighting, serves as a powerful reducing agent in chemical synthesis and metallurgy, functions as an efficient liquid metal coolant in certain nuclear reactors, and supports scientific research and advanced manufacturing processes. Its excellent heat transfer properties, high thermal conductivity, strong reducing ability, and characteristic yellow light emission make sodium one of the most important industrial metals among the alkali elements, contributing significantly to modern technology, engineering, and chemical industries. Potassium is one of the most important S-block elements because of its enormous contribution to modern agriculture and global food production. Although metallic potassium is highly reactive and is rarely used in its pure form, its compounds are among the most valuable industrial chemicals in the world. Potassium is an essential plant nutrient and is one of the 3 primary macronutrients required for healthy crop growth, collectively known as NPK fertilizers, where N stands for nitrogen, P for phosphorus, and K for potassium. The infographic illustrates how potassium supports plant development, improves crop quality, enhances disease resistance, and forms the foundation of the potash industry, making it indispensable for sustainable agriculture and the world's food supply. The largest industrial use of potassium is in the production of fertilizers. Plants require potassium throughout their life cycle because it plays a vital role in numerous physiological and biochemical processes. Unlike nitrogen, which mainly promotes leafy growth, or phosphorus, which supports root and flower development, potassium regulates many essential functions that keep the entire plant healthy. Potassium fertilizers are widely applied to agricultural fields to increase crop productivity, improve fruit quality, and ensure healthy plant growth. Without adequate potassium, crops become weaker, produce lower yields, and are more vulnerable to environmental stress and disease. One of potassium's most important roles in plants is regulating water balance. Potassium controls the opening and closing of tiny pores on leaves called stomata. These microscopic openings regulate the movement of water vapor and gases between the plant and the atmosphere. By controlling stomatal activity, potassium helps plants conserve water during dry conditions while still allowing sufficient carbon dioxide to enter for photosynthesis. This improves water use efficiency and helps crops survive periods of drought. Potassium also plays a critical role in photosynthesis, the process by which plants convert sunlight, carbon dioxide, and water into glucose and oxygen. It activates numerous enzymes involved in photosynthesis and supports the transport of sugars produced in the leaves to other parts of the plant. As a result, plants supplied with adequate potassium develop larger, healthier leaves that capture more sunlight, produce more food, and grow more efficiently. Another major benefit of potassium is the promotion of strong root development. Healthy roots enable plants to absorb larger amounts of water and essential minerals from the soil. A well-developed root system also anchors the plant firmly, making it more resistant to wind damage and environmental stress. Because of stronger root growth, potassium-treated crops establish themselves more rapidly and remain healthier throughout the growing season. Potassium significantly improves crop yield and quality. Crops supplied with sufficient potassium generally produce larger fruits, stronger stems, better grain filling, improved color, enhanced flavor, and longer storage life after harvesting. Fruits and vegetables grown with adequate potassium often have higher nutritional value and better market quality, making potassium fertilizers essential for commercial agriculture. The infographic also highlights potassium's role in increasing disease resistance. Potassium strengthens plant cell walls and improves the overall health of plant tissues, making it more difficult for bacteria, fungi, and other pathogens to infect crops. It also enhances the plant's natural defense mechanisms against insect attacks and environmental stress. Crops with sufficient potassium are generally more resistant to drought, frost, heat, and various plant diseases, resulting in higher agricultural productivity. Another important function of potassium is enzyme activation. Hundreds of enzymes responsible for photosynthesis, protein synthesis, carbohydrate metabolism, and energy production require potassium ions for proper functioning. These enzymes regulate countless biochemical reactions that allow plants to grow, reproduce, and produce food efficiently. Without potassium, many of these essential metabolic processes slow down considerably. The infographic also explains the importance of the potash industry. Potash refers to naturally occurring, potassium-containing minerals and salts that are mined from underground deposits or extracted from salt lakes and brines. The most common potassium minerals include sylvite, which is potassium chloride, and carnallite, which is potassium magnesium chloride. After mining, these minerals undergo purification and processing to produce potassium-rich fertilizers that are distributed worldwide for agricultural use. The industrial production of potassium fertilizers begins with potash mining. Large underground deposits are excavated using modern mining equipment, while some deposits are extracted by solution mining, where water dissolves the potassium salts before they are pumped to the surface. The extracted materials are then purified, processed, and converted into commercial fertilizers such as potassium chloride, potassium sulfate, and potassium nitrate. These fertilizers are transported to farms around the world, where they are applied to crops to improve agricultural productivity and support global food production. Potassium compounds are also used in several other industries besides agriculture. Potassium hydroxide is widely used in the manufacture of soft soaps, detergents, alkaline batteries, biodiesel production, and industrial cleaning agents. Potassium nitrate is used in fertilizers, fireworks, explosives, and food preservation. Potassium carbonate is employed in the manufacture of specialty glass, ceramics, soaps, and certain chemical processes. Potassium permanganate serves as a powerful oxidizing agent used in water treatment, chemical laboratories, and medical disinfectants. Although these industrial applications are important, fertilizer production remains by far the largest use of potassium worldwide. The infographic emphasizes several key advantages of potassium in agriculture. It promotes healthy plant growth, increases crop yield, improves fruit and grain quality, enhances resistance to diseases and drought, supports photosynthesis, strengthens root systems, activates essential enzymes, and contributes to sustainable farming practices. These benefits make potassium indispensable for feeding the world's growing population. The complete industrial pathway begins with potash mining, followed by potassium extraction, fertilizer manufacturing, agricultural application, healthy crop growth, and finally increased food production. This sequence illustrates how naturally occurring potassium minerals are transformed into valuable agricultural products that directly support global food security and sustainable agriculture. Although metallic potassium itself is extremely reactive and must be stored under mineral oil or an inert atmosphere to prevent violent reactions with air and water, its compounds are stable and safe when handled properly. Because of this stability, potassium fertilizers can be transported, stored, and applied efficiently on farms across the world. Potassium is one of the 3 essential macronutrients required for plant growth and is the foundation of the global fertilizer industry. Through the production of potash-based fertilizers, potassium improves root development, regulates water balance, enhances photosynthesis, activates enzymes, strengthens disease resistance, increases crop yield and quality, and supports sustainable agricultural practices. The potash industry transforms naturally occurring potassium minerals into fertilizers that nourish crops and help feed billions of people worldwide. Although metallic potassium has limited direct industrial use because of its extreme reactivity, its compounds are among the most valuable agricultural chemicals and play a vital role in ensuring global food production, environmental sustainability, and modern farming. Magnesium is one of the most important S-block elements because it combines an exceptionally low density with remarkable strength, making it one of the lightest structural metals used in modern engineering. Although pure magnesium is highly reactive, it forms strong and lightweight alloys that are widely used in aerospace, automotive engineering, electronics, and many other industries. The infographic illustrates the major industrial applications of magnesium, including aircraft manufacturing, fireworks, historical photography, and lightweight engineering materials. These applications arise from magnesium's unique combination of low weight, high strength-to-weight ratio, excellent machinability, corrosion resistance in alloys, and its ability to produce an intense white light when burned. One of the largest industrial applications of magnesium is in the aerospace industry. Every kilogram of weight saved in an aircraft reduces fuel consumption and improves overall efficiency. Magnesium is about 1/3 lighter than aluminum and nearly 4 times lighter than steel, making it an ideal material for manufacturing lightweight structural components. Instead of using pure magnesium, engineers generally use magnesium alloys, which combine magnesium with elements such as aluminum, zinc, and manganese to improve strength, durability, and corrosion resistance. These alloys are used to manufacture aircraft parts, helicopter components, spacecraft structures, and various aerospace equipment. By reducing the overall weight of an aircraft, magnesium alloys increase fuel efficiency, improve payload capacity, and lower operating costs. Magnesium is also widely used in the automotive industry, where manufacturers continuously seek lighter materials to improve vehicle performance and reduce fuel consumption. Magnesium alloys are used to produce steering wheels, transmission housings, engine components, seat frames, dashboard supports, wheels, and various structural parts. In electric vehicles, reducing weight is especially important because lighter vehicles require less energy to travel the same distance, thereby increasing battery range. The high strength-to-weight ratio of magnesium makes it an excellent choice for modern transportation systems. Another important industrial application of magnesium is in lightweight engineering materials. Magnesium alloys are increasingly used in bicycles, motorcycles, racing cars, drones, robots, laptops, cameras, and portable electronic devices because they provide excellent mechanical strength while keeping the overall weight very low. Magnesium is also easy to machine, allowing manufacturers to produce complex shapes with high precision. This combination of strength, lightness, and machinability makes magnesium an attractive material for advanced engineering applications. One of magnesium's most fascinating properties is its ability to burn with an extremely bright white flame. When heated to its ignition temperature, magnesium reacts rapidly with oxygen in the air according to the reaction. Two bangs, pulse O2, 2 MAGYO. This reaction releases a tremendous amount of energy in the form of heat and brilliant white light. Because of this intense brightness, magnesium is widely used in fireworks, flares, signal devices, emergency rescue equipment, military illumination flares, and pyrotechnics. Fireworks containing magnesium produce dazzling white sparks that are visible over long distances, making public celebrations and displays much more spectacular. The infographic also highlights the historical use of magnesium in photography. Before the invention of modern electronic flash units, photographers used magnesium flash powder or magnesium flash bulbs to illuminate dark environments. When ignited, magnesium produced a brilliant flash of white light that was bright enough to expose photographic film. Although electronic flash technology has now replaced magnesium flash in modern cameras, this historical application demonstrates the remarkable light-producing capability of magnesium. Magnesium is valued in engineering because of several important physical properties. It has a very low density, making it one of the lightest structural metals available. It possesses an excellent strength-to-weight ratio, allowing engineers to design lightweight structures without sacrificing mechanical strength. Magnesium alloys also exhibit good vibration damping properties, which help reduce mechanical vibrations and noise in vehicles and machinery. Additionally, magnesium can be cast, machined, and recycled efficiently, making it economically attractive for large-scale manufacturing. The infographic also emphasizes the key advantages of magnesium in industrial applications. Its lightweight nature reduces transportation costs and improves fuel efficiency. Its high mechanical strength provides reliable structural performance. Its excellent machinability allows the manufacture of intricate components with high precision. Its brilliant white flame makes it valuable in fireworks and emergency signaling devices. These advantages have made magnesium one of the most important engineering metals in the modern world. The industrial production pathway begins with magnesium extraction from minerals such as dolomite and magnesite or from seawater. After extraction and purification, magnesium is processed into pure metal or alloyed with other elements to improve its mechanical properties. These alloys are then used in aerospace engineering, automotive manufacturing, electronics, transportation systems, and numerous lightweight structural applications. Through these industries, magnesium contributes significantly to improved energy efficiency, reduced fuel consumption, and technological advancement. Although magnesium has many advantages, it must also be handled carefully because finely divided magnesium powder and thin magnesium ribbons ignite easily and burn at extremely high temperatures. Magnesium fires cannot be extinguished with water because hot magnesium reacts with water to produce hydrogen gas, which may intensify the fire. Instead, special Class D fire extinguishers or dry sand are used to control magnesium fires safely. Magnesium is one of the lightest structural metals and plays a crucial role in modern engineering and industry. Its exceptionally low density, high strength-to-weight ratio, excellent machinability, and corrosion resistance in alloy form make it indispensable for aircraft, automobiles, lightweight engineering materials, and advanced manufacturing. Its ability to produce an intense white flame has also made it valuable in fireworks, emergency flares, and historical photography. Together, these remarkable properties have established magnesium as one of the most important industrial metals, contributing to safer transportation, greater fuel efficiency, modern aerospace technology, and innovative engineering solutions across the world.